Now I'm going to summarize for you estimation techniques. So assume you have a sample and you're interested from which distribution it comes from. Basically, you want to know what parameters are the correct ones for this particular sample that you observe. Example, if you have a sample x1 and xn to xn and you have a certain PDF that describes the sample, and it might come from either normal distribution with parameters mu and sigma squared, or Poisson distribution with parameter lambda, or any other distribution. And you're interested in what are the correct values or the best estimators that you can get for this distribution. So there are three different techniques that we were talking about during the lecture. First is the method of moments. Method of moments is probably the easiest technique that we can use in order to estimate the parameters. The idea behind the method of moments is very simple. What you're doing is you're simply setting the k population moments to equal to the k sample moments. I say k because k is the number of parameters that you want to estimate. If, say, we are talking about the Poisson distribution, then you will only need the first moment, which is the mean. If we're talking about the normal distribution, which has two parameters, we'll need to consider two sample moments. So the mean as well as the expectation of x squared. So for the example of the normal distribution, we have a vector of parameters theta, which is mu and sigma squared. So we're simply setting the sample mean x bar equal to the population mean x. And we know this is nothing but just the sum of all the observations divided by the total number of observations. Since we estimate in two parameters, we also need the second moment equation. So expected value of x squared, which we know can be represented as the variance plus the squared mean. And this is given by the sum of xi squared over the total number of observations. Now, if you solve these two equations with respect to the mu and sigma, then you will get the estimates for the mu, and you'll see that this is nothing but x bar, which is the sum of x, right? It's just evident from the first equation already. And if you solve the second equation, then you will see that the best estimate for the sigma squared will be just the sample variance scaled by the factor n minus 1 over n. The second estimation technique that we are talking about is the maximum likelihood estimation. So maximum likelihood estimation is asking you to first compute the so-called likelihood function. And the likelihood function is nothing but the joint distribution or joint density from your data. Okay? And typically, we assume that our observations or random variables are independent. This simple assumption allows us to write the joint PDF simply as a product of individual PDFs. Okay? And if we're interested in estimating the parameter theta, what we are doing is we are maximizing this joint PDF, which is also called likelihood, with respect to the parameter theta. By doing this, we are finding such an estimator theta that provides the most likely outcome for our sample. The maximization is performed in a very standard way, so depending on how many parameters theta you have to estimate, you will have the same number of equations. Say, for example, if you had to estimate only two parameters, so you had only theta 1 and theta 2, then you would take the derivative of the likelihood with respect to theta 1 and set it equal to 0. And you will do the same with the derivative with respect to theta 2 and set it equal to 0. And you will get your parameters theta 1, theta 2. In practice, it is easier to take the logarithm of this likelihood, because in this case, the logarithm of the product becomes the sum of those logarithmic densities, which allows you to easily integrate with respect to the parameters. Okay, so we call it also the log likelihood. Okay, and we denote it by small l. Okay, this is just the log of the likelihood. Okay, and then you can perform the same procedure. So you're just maximizing the log likelihood with respect to theta. So you'll take in the derivative of the log likelihood with respect to each of the parameters that you want to find. Also, please don't forget that since we're interested in the maximum and not the minimum, we will also have to check that the second derivatives of the log likelihood with respect to the parameter are negative. Okay, remember, negative second derivative means our optimum is in fact the maximum. Now, the third estimation technique, which is potentially perceived as the most difficult one, is the Bayesian estimation. And the Bayesian estimation technique suggests that given the sample with a certain distribution, okay, we can find the posterior distribution for the parameter as the integral. Sorry, the integral is in the denominator as this distribution. We also call it the likelihood multiplied by the so-called prior distribution p theta divided by the joint distribution of your x. So it's an integral of x given theta of your sample evaluated with respect to this posterior density. Okay. So you can see that in fact this integral, since you're taking an integral with respect to theta, you're integrating it out. In fact, it will not depend on theta, okay, which allows you to write the posterior density as the product, or we say this is proportional to the product of the likelihood times the prior density. Okay, so this is prior, this is likelihood. So prior is typically obtained from the previous experience, either expert's opinion or say someone has estimated theta using comparable data, but for a different sample frame. So basically this is something that you believe is a good starting point. And the likelihood is basically given by your data. So if your data has a particular distribution, you just plug in the density from obtained as a likelihood for your sample. So there are two different ways to find the estimator. You either proceed using this method, so which is the most tedious one because it will require you to evaluate the integral in denominator, and then you will compare your posterior to the resulted expression, which is hopefully one of the known distributions, or since the posterior does not depend on the denominator of this posterior, so this part is free of theta, you can write it as the product of the likelihood times the prior. So we say it's proportional, so that means proportional up to a certain constant. And this is a simpler method. It doesn't require you to compute the integral. You can just multiply the prior and the likelihood, and you will find a certain expression, and you can check your Orange book to see what known distribution this can be. So this is typically the simpler way that doesn't require you to compute the integral.